Welcome to The Explainer. Today, we're going to decode some really fascinating research about the secret signals our electronics are constantly sending out.
It sounds a little bit like science fiction, right? But get this. Every single one of your electronic devices, yeah, I'm talking your laptop, even your smart toaster, is constantly emitting these invisible electromagnetic waves. They're just leaking these little signals out into the world, completely unintentionally.
So a team of researchers decided, hey, what if we tried to listen to those signals? They set up this really clever experiment to see if they could actually capture and, understand these whispers. And the biggest secret of all? The encryption key. Okay, let's really dig into how they pull this off.
All right, so this whole idea brings us to a really clever type of hacking. And the interesting thing is it's not about attacking the software. Not at all. It's about going after the physical device itself. Yeah, it's called a side channel attack, and it's exactly what it sounds like. It's attacking from the side. It's all about grabbing those little clues the hardware accidentally gives off while it's just, doing its thing. It's got nothing to do with finding bugs in the code. It is, quite literally, about listening to the machine.
Okay, here's a great way to think about it. A conventional hack, that's like taking a sledgehammer to a safe. Just brute force. But a side channel attack, oh, that's way more elegant. It's like being a master safecracker, with your ear pressed against the door, carefully listening for the tiny clicks of the tumblers to figure out the combination. See the difference? One's a noisy, direct assault. The other is all about subtle, clever eavesdropping.
And get this kind of thing used to be incredibly difficult and expensive. We're talking massive, government-level operations, like the codebreakers working on the Enigma machine back in World War II. But today, well, thanks to modern tech, it's become surprisingly easy and cheap. We're talking shockingly accessible.
Okay, so the researchers had their method down. They knew how they wanted to listen. But what were they going to listen to? They needed a target. And for this experiment, they picked a very specific kind of encryption to go after. They went after a cipher called Present. Now, Present is super interesting because it was designed specifically for all those tiny, low-power devices that make up the Internet of Things. Your smart home sensors, little connected gadgets, that kind of stuff. And the part they were really interested in was its 80-bit key. You can think of that as a short secret password that keeps these little devices secure. And look, this isn't just some abstract academic thing. The security of a cipher like Present is a huge deal. I mean, think about it. Understanding its weaknesses is absolutely vital if we're going to keep our super-connected world safe.
All right, now for the really cool part, the investigation itself. So, how in the world do you actually eavesdrop on a microchip?
Well, it all comes down to a really basic rule of physics. Whenever electricity zips through the tiny circuits on a chip, it can't help but create these little electromagnetic waves. So the researchers' big idea was, what if we could analyze those waves and find patterns that are tied directly to the secret key?
The method they used has a fancy name, Correlation Electromagnetic Analysis, or CEMA for short. But really, it's a pretty straightforward three-step process. First, you just get the device to encrypt stuff, over and over again. While it's doing that, step 2, you use a magnetic probe, which is basically just a tiny antenna, to capture all those EM waves it's giving off. And then, for the final step, you crunch the numbers. You use some statistical analysis to find these little patterns, these correlations, that connect the shape of the waves back to the secret key.
And you might be picturing some crazy super-secret spy lab for this, right? But the reality is, the setup was surprisingly simple. We're talking standard, off-the-shelf lab equipment, an oscilloscope, a few special probes. That's it. No James Bond gadgets needed for this high-tech eavesdropping.
So they've got their setup, they're carefully listening in, and then they get it. A breakthrough.
And here it is, the big number, 80%. Just by listening to those faint whispers from the chip, they managed to recover a whopping 80% of the secret encryption key. So, to put that into perspective for you, an 80-bit key is basically made of 10 bytes of information. And these guys managed to figure out 8 of those 10 secret bytes, just from the radiation. They never touched the software, never even tried to crack the encryption code itself. Wild.
And here's what's truly mind-blowing, how efficient their method was. They got this incredible result using only 256 recordings, or waveforms. Now, just to give you some context, earlier attacks trying to do the same thing needed over 12,000 waveforms. I mean, the difference is just staggering.
So you're probably wondering, how did they actually see the key? Well, when they analyzed the data, they looked for these very specific spikes and dips on their graphs. And when they found one, a sharp dip, it was like a big flashing sign. Each one was basically a little piece of the key's secret signature being broadcast out for them to find.
Okay, so grabbing 80% of a key is a huge deal for an attacker. No question. But what does that really mean? Are our devices actually secure or not?
Well, here's the thing. Getting most of the key, like that, makes the rest of the job ridiculously easy. Trying to guess the whole 10-byte key from scratch, a brute force attack, that's pretty much impossible. It would take ages. But if you already have 8 of the 10 bytes, guessing the last 2, well, for any modern computer, that's child's play. It's practically instantaneous.
But, and this is a big but, the researchers' final take was pretty balanced. They said, look, our attack is really powerful. For sure, it's the most efficient one we've ever seen. But it wasn't perfect. Crucially, those last 2 bytes of the key didn't leak out. So their final conclusion was that in a real-world situation, with all the proper security features turned on, the present cipher is probably still strong enough for what it's designed to do. And that really leaves us with this big, lingering question, doesn't it? As we keep connecting every little thing in our world, as we fill it with trillions of tiny computers, the challenge isn't just about protecting software anymore. It's about figuring out how to deal with this invisible language our hardware is speaking, these constant whispers that our machines are putting out into the world.